In this video, we're going to take a look at a standard sine equation and see if we can figure out or better understand how each of these values, these a, b, c, and d values, affect the attributes of the sine function. Now we're looking at a sine function here, but the values affect a cosine function and other periodic functions similarly. There are nuances and differences, but most of what we learn here is transferable to other periodic functions. I notice this equation looks an awful lot like the transformation equation that we've been using all year, and there's good reason for that. It's nearly exactly the same. The only difference in a periodic function is we have a different name for some of these things. But if we look at the standard sine equation that we have graphed out here, and we start to change this a value, you can see what happens. In the past, we referred to this as a vertical dilation. We vertically stretch the function, or when we make it negative, we reflect it over the x-axis and we stretch it in the other direction. So the difference in a periodic function, instead of referring to that as a vertical stretch, we refer to that attribute as the amplitude of the periodic function. The b value of this function, we haven't used this b value too much in other function families, but you can see it becomes very important in a periodic function because as I make this b value larger, the function is compressed horizontally, or as I make it negative, it reflects in this case over the y-axis and then begins to compress from the negative direction. This horizontal compression affects two attributes of a periodic function called the frequency and the period. C value does the same thing. This is the value attached to the variable x, or sometimes on a periodic function, we'll refer to that as theta. And that C value has the effect of translating the function along the x-axis. So it's translating it horizontally. Now, again, the effect here on a periodic function is the same as it has been on all the other functions we've looked at. The difference here is instead of calling it a horizontal translation, we refer to it as a phase shift. And in fact, on a periodic function, you can see we can actually phase shift the function so that it's on top of itself and looks exactly the same. Now we'll phase shift that back to 0 and take a look at letter D, which we know to be vertical translation. Simply moves the function up and down the y-axis vertically. And all year long, we've been referring to this as vertical translation. The difference with a periodic function is we refer to this as, instead of vertically translating, we'll refer to that value as the midline. Sometimes you'll hear it referred to as average, sometimes equilibrium, but most of the time we'll refer to this d value as the midline of the function. Now let's take a look at these in written form and see if we can continue to make sense of it, and then we'll close it out with one final look at Desmos. We have two different and both very common forms of a sine equation here, and we want to go through the similarities and differences when you see them in these two forms. We'll notice that the difference here is on the left in the blue, this b value has been factored away from this quantity x minus c, and on the right or in the purple, you can see that the b value is integrated with the x variable or the angle itself. So what are the similarities? In both forms of the equation, we simply read the a value. The amplitude is equal to the absolute value of the a value. And in both equations, we determine the midline by looking at the d value. In both equations, we determine the period, and we often use a capital letter T to denote period. We determine the period by taking 2 pi divided by the absolute value of this b value. Now, phase shift is where things change a bit. On the left in the blue, we can read the phase shift directly by looking at the value of this c. We'll remember that's negated. On the right, we actually have to divide c by b in order to get the phase shift. Now, phase shift is often denoted by the Greek letter phi. And we're going to go through a couple of examples, or an example here, and see if we can demystify this a bit. If we look at these two equations are actually exactly the same thing. On the left, if I simply distribute this 2 into the parentheses, I am going to end up with 3 sine, and then I take 2 times x, which gives me 2x, and I take 2 times pi over 4, which gives me 2 pi over 4, or simplified 2 pi over 2, and I add the 1 on the outside, and you'll notice I have developed an equation that is exactly the same as this one. On the right, I can do just the opposite. I can bring down the y equals 3 sine, only now, instead of distributing that 2, I'm actually going to factor this 2 out. And if I factor that 2 out in the parentheses, I end up with 2 times, well, 2x divided by 2 is x. Pi over 2 divided by 2 is pi over 4. And then I add my 1 on the outside. And you'll notice I'm right back to the exact same equation I had on the left. Now let's take a look at these same equations on Desmos. Okay, so here we have the exact same functions represented graphically. In this first one, which is highlighted in green on the graph, we're in the form of bx minus c. In this one, which is the exact same equation, we are in the form of b times x minus c, but you'll notice those are the exact same function. So let's see how we can quickly evaluate these. We can look at the midline. We're looking at this number here, plus 1, or what we would typically know as the vertical translation, represents a midline of y equals 1. So no need to calculate there. We can simply read it directly from the function. The amplitude of the function we read by looking at the number 3, the a value of the function, and we're taking an absolute value. This a value can be negative, but the amplitude is always going to be positive, and the amplitude is simply represented by the uppermost value of the function minus the midline, the distance from the midline to the uppermost value. The period of the function we can take a look at in a couple of different ways. We can look along the midline and say, well, it's starting right here at the midline and it completes one full cycle right here at the midline. This value is 5 pi over 4. This value is pi over 4. And when we subtract those two, we get a period of pi. Now we also know we can look back up here at the function and say that 2 pi divided by 2, or 2 pi divided by the absolute value of b, is going to give us the period. Other ways of visually representing the period, we could look at it along the midline. We can look at it from peak to peak. We can look at it from trough to trough. It's all exactly the same distance. It's going to be pi. Now to evaluate the phase shift, we decided we shifted this by pi over 4 to the right, and we can get that number directly from this form by looking at this pi over 4, or we can get it from this form by taking c divided by b. Pi over 2 divided by 2 is pi over 4. And that distance is represented here along the midline. That's a distance of pi over 4. Without that phase shift, the function looks like that. And we'll notice it's crossing the y-axis directly at the midline, y equals 1. So the effect of that phase shift is to move it to the right by a distance of pi over 4. All right, so just learning how to read this function, we can figure out the midline, we can figure out the amplitude, we can figure out the period, and we can figure out the phase shift.